Hi, I've put together this quick video to help those of you that are struggling a little bit with this assignment to describe how you might go around completing the document that you have in front of you. This is, of course, in the assignment section of Blackboard, you'll find this document along with a little bit of supporting material. Okay, so what we're asking you to do basically is take a look at the yellow parts of these that are highlighted in yellow, this document, and those are going to be mainly the areas of interest for you. So, for instance, in this situation, we had a 6-inch galvanized iron duct in class, diameter 6 inches, zero point 0.5 feet, same thing. What we're asking you here is number one, tell us what the area of this duct is in square feet. Okay, I even gave you a little bit of a reminder that the diameter is 0 0.5 feet, so you should be able to figure out what the area is. Of course, pi r squared, radius squared. Okay, so now once you've done that, in order to take readings, we know that the airflow through the duct is not uniform. It's actually faster in the center of the duct than it is at the areas closest to the side walls of the duct itself because friction on the fluid as it's moving through the ductwork. It's kind of like instead of a straight line moving through, it's kind of a parabola moving through with the highest velocity in the middle. Okay, so what we're asking for you to do here is to give us the depths that you would measure in inches for this particular duct. Now, we've helped you out with a little bit. There's a JPEG that's on Blackboard along with the assignment where it'll tell you, for instance, that these are the 10 measuring points, the distances you have to be in from the side of the duct when you're measuring the velocity at 10 different points, either vertically and horizontally or horizontally, so you're measuring velocities at equal areas. So for instance, the first one is, if we're starting from this side, the first one is 0.949 times the radius of the duct. That's how far in it has to be. The next one is 0.837 radiuses in from this side of the duct. And you can, from this, you can deduct what all these different distances would have to be that you're going to have to be in. So first of all, you would put these depths, what are the depths are that you would calculate from those numbers. Then you would calculate the velocity at each one of these different points, at the center line for each one of these different points. And what is that velocity equal to? Velocity is equal to 4,005 times the square root of the velocity pressure, measures of inches of water gauge. So you have the velocity that I've given you. Okay, if you did measurements in the lab, use your own velocities. If you didn't successfully do measurements in the lab, you can use the ones that I've given you here. You can just overwrite these or put them in Excel and work from them in Excel. This is a Word document, so you can change these. Okay, so if it were a 0.1 inch of water gauge, the velocity would be 4,005 times the square root of 0.1, which is 0.01, 0.01, I think, yes, 0.01, right? So this would be 0.01 times this would be 40 CFM and so on and so forth. I think you can actually do your own calculations there. Okay? So you calculate this for each of these velocities and then add them up down, put the velocity subtotal down here and give me the average velocity here. The center line velocity I guessed at being this amount. Apparently it's going to be a lot different than that amount, but you can ignore that for now since you're not being asked that anyway. Okay, so the average velocity, you would calculate that average of these 10 numbers and put it in there. The cross-sectional area of the duct you would put in here, and the volumetric flow rate, how many CFM is going through there. And you can use the formula that Q, the quantity of air, is equal to the velocity in feet per minute times the cross-sectional area of the ductwork, or your 6-inch ductwork, or your 0.5-foot diameter ductwork in square feet. Okay, so got to have this in square feet, got to have this in feet per minute, multiply them, gives you the volume of air that's moving through here. So you should be able to take care of that, I think. The next part is a part where we looked at the performance difference in a round hood where air could get sucked around easily around the side. So you lose some of the air that you want to intend to do your work of capturing the contaminant in front of the hood opening, right? You lose some of that. Flanged hood helps you lose less of it. So I put down numbers myself here, you can use either my numbers, or if you did the measurements in class, you might want to put in your numbers. Typically, I think you're going to find that with a flanged hood, that you'll have higher velocities at each distance than you would if you had a plain hood. So that's one lesson here. The other lesson here is that the capture velocity dramatically decreases with an increase of distance from the opening of the duct. So even just at 3 inches, we had 350 feet per minute. Even just at 12 inches, we're already down to 75 feet per minute. So we lost an enormous amount of capture velocity. So you might want to rephrase that in your own words and put them in here in comments and instruments that we use to do this. I think we used a thermal anemometer or a vein anemometer for that. Okay, and here we're simulating a couple of lab hoods. Now with lab hoods, just so you have this document, as I was saying, with lab hoods, what we're looking at with lab hoods is when we're opening up, when we're measuring the velocity that's coming in front of the lab hood, we're looking at the height that it's open, the size of the opening of the lab hood, the height, and the width of it. So in this case, we've divided the opening, the face of the lab hood into 4 areas, four rectangles, and we would measure the center of each of these rectangles to get an average velocity. Okay, so we would take these different velocities, 110 feet per minute, 120 feet per minute. We would find the average of those velocities. Okay, so our average velocity would be the average of these 4 numbers. So that's our average velocity. Now the cross-sectional area of this duct is just simply the width of the duct, width of the opening times the length of the opening, and we give it here. So you can calculate the area in square feet, right? So you have the velocity in feet per minute, the area in square feet. So then you can calculate the volume of air that is being pulled into this hood. And in this, we've done a little bit more accurate reading of an opening for a lab hood. And instead of using only 4 areas that we measured, we broke it up into 8 rectangles. And each of the rectangles, we took a velocity in the center of the imaginary rectangle, and we took an average, and you can calculate average velocity here. And again, different length and width, you can calculate what your average velocity is from the average of these numbers, and you can calculate your area based on the length and the width, and you can calculate your quantity of air being moved. Quantity is equal to the velocity times the cross-sectional area. Okay, and you can comment on what instruments that you used when we did that in class. Okay, so last thing is I'd like to ask you to answer some questions on this assignment. So for instance, what are the velocity pressure measurements taken, why are we taking these velocity pressure measurements in the ductwork as a set of points across a traverse? Why not just take 1 reading? Why are we taking 10 readings across the ductwork? And you can let me know why you think that we're doing that instead of just taking a single reading. What's the maximum sash height that you can use a lab hood that is 6 feet wide? What's maximum sash height you can use in a lab hood that is 6 feet wide with a quantity of air moving of 1,000 CFM, and assume the capture velocity is 125 feet per minute. Now, you don't have to listen to me if you want to do this problem completely on your own, but if you're struggling with it, consider this. We know that the velocity we want across the face of this duct is 125 feet per minute. And we know we have 1,000 cubic feet per minute that we have available to use to pull air into this duct. So we have a velocity and we have a quantity, right? So if we have a velocity and a quantity, if we want to get a velocity of 125 feet per minute, given that much air, we can calculate that area. Q is equal to V times A. So Q is equal to V times A. A, which we don't know here, we do know V and Q, right? We can move V over to the side, so Q over V. So the quantity of the cross-sectional area that we can have is going to be 1,000 cubic feet per minute divided by 125 feet per minute, right? Is going to leave us with some number. Okay, I think it's going to be. I'm not going to tell you what that number is. Might be. Let's see. 7. I'll leave it up to you to figure that out. I think might be 8 square feet. Well, if the laboratory hood is 6 feet wide, how high in feet or inches can it be? Does it have to be? How high does it have to be to give you a cross-sectional area of 8 feet? So you should be able to figure that out. Okay, even without my help there. Okay, but if you need it, you can take that as a little bit of a hint. What does the orientation of the pitot tube affect the velocity pressure readings, and does it affect the static pressure readings? Well, we remember when we were measuring the velocity pressure. Velocity pressure is that, for instance, if you're standing in a breeze outside, the static pressure is the atmospheric pressure, which is acting on you the same in all directions, right? It's just the pressure from the atmosphere. It's acting on your sides the same way it's acting on top of your head, and so on and so forth. So that should be a hint as to whether the orientation is critical. But the velocity pressure, that's like the wind hitting your face, that has direction. So maybe that's a hint to that particular question. What's the relationship between the total pressure and the velocity pressure? You can go back to the slides and take a look at that and tell me what the mathematical relationship is between those two things. Okay, and name two organizations that have standards for testing or maintaining laboratory hoods. And one of the things that you can do here is you can just simply go to Google and you can Google, let me see, I can't get this stuff work here. Okay, laboratory hood. Okay, let's see what we come up with here. I'm going to go to, I don't see that. It's a lot of people are into this as a profession for money, but I'm going to open up this one. This is an educational system, so I'm going to open this up. And as a reference, first of all, you could put OSHA down. OSHA does have standards for this as well. But exhaustive, we have at I see ANSI and AIHA and so on and so forth. Actually, I bet you if I go to the end of this, if there's references, let's see if there's references here. Do I see any references now? They have an attached document here. Maybe here we go. ASHRAE, method of testing the performance of laboratory hoods. American Industrial Hygiene Association, National Laboratory Standards. As you're going through this, you might say, well, gee, now that I know that standard exists, let me go to their website and take a look at, at that standard, or maybe some summary of that standard if I have to pay for it. Maybe I don't want to pay them $100 to download the whole standard, but at least let me take a look at this or Google that standard on here and see if I can't get any observes from it and learn a bit about it. Okay, so there are some organizations that have standards for specifically how to design and how to test the performance of laboratory hoods. Get that out of the way. And finally, at the end here, what is the difference between a bolometer and a velometer? And we went over this in class, but just to remind you, a velometer measures airspeed. The anemometer is a form of velometer, right? We had a thermal anemometer in class. We also used a pitot tube. In this one, it's connected to a device that will actually do the conversion from velocity and static pressure or total pressure to velocity for you. Here's a guy standing up on a ladder. He's drilled a hole in the hood. He's going to use either a velometer or a pitot tube to measure the velocity in that duct, right? A bolometer, on the other hand, measures volume of airflow, cubic feet per minute. And a lot of times, most common use here is typical one. Most common use for those is the measuring the volume of air coming out of diffusers in a indoor air quality situation, in an indoor HVAC system, distribution duct system. This guy is actually, there's a little gauge on here you can read the volume of air. He's holding it up over a diffuser. It's got a little rubber seal on it, a foam seal on it, helps it seal up so it captures all the air coming out of the diffuser. I used to do this standing on a rickety ladder. I wish I had known that they sold poles that you could raise them up on in order to do this. Would have saved me a few close calls. Okay, so I mean that's what bolometer again, velocity, velometer measure velocity. Okay, so I think that's pretty good. Just complete the document, upload it. You'll see the images I showed you are on Blackboard with the assignment. Okay, hopefully that helps you if you needed it in completing this assignment.